Okay, so let's quickly just go over the steps of this derivation of elastic potential energy in a longitudinal strain case. So if we stretch this longitudinal body of natural length L to a final elongated length of or compressed length, whichever be the case, of L plus delta L or L minus delta L, then in the process, as we are changing the elongation x from x equal to 0 to x equal to delta L, the work done by the external agent, which is the work done against the internal restorative force or the internal elastic conservative force, that is equal to the potential energy stored in the system. So in this case, if we take the body from its natural state, or in this case, natural length, to a case where it is strained, or in this case, to a case where it is elongated or compressed by delta L, then the energy stored in the system, the absolute potential energy, is nothing but the work done by the external agent in order to take it from natural shape to deformed state. Whereas if it was already in some deformed state, then the change in potential energy would be the work done to go from the initial deformed state to the final deformed state. But if we started from the natural shape where there was no deformity, then we can say that the absolute potential energy at some state of deformity, that itself is equal to the work done from from natural shape to the deformed state. So this is how we get the formula for absolute potential energy of this kind of material as a function of delta L, where delta L is the amount of deformity. Now, one interesting thing we'll see here is that if we divide this expression of potential energy with the volume of the body, that is the natural volume, then we get elastic potential energy per unit volume. So that we can denote with a simple small e. That is elastic potential energy per unit volume. So we'll take the volume as E into L. So we can see that this becomes this, or it is half of Young's modulus into strain square, or we can also treat it as half of stress into strain, because modulus of elasticity into strain is nothing but stress. So this becomes a useful idea here, that potential energy density is equal to half of stress into strain. And notice now that it's a universal formula. Though we have done the derivation above only for the longitudinal stress and strain, but this can be applied universally to case of shearing as well as a case of volumetric stress and strain. So this formula, in addition to the formula for Hooke's law, that is stress upon strain is equal to Young's modulus, will be applied in an instantaneous kind of situation, or for a differential element when we have a case of variable stress. Like the case of the rod hanging under some weight that we discussed last time. Both the formula, that stress upon strain is equal to Young's modulus, that is Hooke's law, and energy density formula both can be applied a differential element and then integrated to calculate the deformity or the total elastic potential energy, whatever be the case. So we'll see an example of this next because this is very important from the JEE Advanced point of view. So for example, if we have a situation where once again we have that standard metallic rod of given natural length and given area of cross section, made of material of Young's modulus Y. Now suppose we subject this to a condition where it is made to rotate about a fixed axis perpendicular to its length and passing through one of its ends. It's made to rotate like this with an angular speed omega naught. So as a result of that, it will be in a elongated state now. So now if we consider inside the rod any point P, which is at a distance of, let's say, x from the axis of rotation. So this is the state of the rod. Now we want to calculate stress as a function of x at the point P. Then we want to calculate the elongation. And we want to calculate the elastic potential energy. So in this case, it will be the centrifugal force that is acting outwards on the particles of the rod as it is in this rotational state, which will be causing the deformity in the first place. Okay. And that will be causing elastic potential energy to be stored and the rod to be in a state of slight amount of extension as even as it is rotating uniformly about a fixed axis. So we have to calculate these by using this concept above, that both Hooke's law and the formula of elastic potential energy per unit volume or energy density formula, potential energy density formula, can be applied to a differential element of a material when there is non-uniform stress. And then we can integrate that over the entire body or the entire material to calculate the required quantities. So just try this out with it. Yeah, so let's work this out now. Yeah, we'll have to assume the mass of the rods, Nikita. That's correct. So first thing is assuming some mass of the rod, how we'll find the stress as a function of x. So there's a couple of ways of doing that. One is that you just assume that you have this portion which is of length L minus x. And you're making the free body diagram of this portion. So as this portion is rotating about this axis, its center of mass is experiencing a centrifugal force like this. Okay. And there is tension here at the point P. Point P. Okay. So this centrifugal force will be equal to mass of this much portion, let's say m prime, into omega square into position of the center of mass with respect to the axis. So this is the center of mass of this much portion. This will be this. So mass of this much portion, let's say PQ, where Q is this point. So m prime is equal to linear mass density into L minus x. And RCM, you can see, will become x plus L minus x by 2. So the centrifugal force which is acting. So in the rotating frame, we see this object at rest. So this is the mass into this angular speed square into so we get tension which balances the centrifugal force. So this is tension as a function of x. So you can notice something interesting here at x equal to 0, that is the axis of rotation. The tension is equal to which is basically the centrifugal force on the midpoint or COM, the full rod, whereas x equal to L, tension is 0. That's how the tension is varying. So first part's answer, stress. Stress is often written with the symbol sigma, longitudinal stress, that is. So it is this is the stress as a function of x. So hope this is clear. Okay, now there is another way of deriving this stress also, but that is like a little bit lengthy. Explain it to you how that works. And also understand it this way, that we consider an element which is of thickness dx, okay, which is at a distance x. So this element is of now mass dm, which will be m by l into dx. Okay. Now on this element there will be centrifugal force acting. So that centrifugal force is dm omega square x. Okay. Because it's rotating like this. Okay. So in the rotating frame. Now if we assume that tension is a function of x, so T is equal to T at x equal to x. T is equal to T plus dt at x equal to x plus dx, where dt is equal to like this. Here we don't need to write because it's just a function of x, so this is not really necessary. We can just write that dt by dx is gradient of tension, because tension does not depend on any other variable, only on x. Okay, so if the tension from this side is T, because this is x, okay, from this side we'll take it as T plus dt. So from the free body diagram, you'll get that dt is equal to minus of this. Okay, so actually the tension of this side is more. So anyhow, so dt will become minus of dm omega square x. So this is how the tension is varying with respect to x. Now when we do this integration, the problem is instead of x equal to 0 now, we will take it from x equal to x, where the tension is unknown, to x equal to L, the end of the road where we know the tension is 0. Okay, so using upper limit at x equal to L, because we know that tension is equal to 0 at the extreme end of the road. So use that limit here. So 0 minus t will become minus m by 2L omega square, L square minus x square. So we get that same formula of tension that we got. And from that we get the same formula of stress. So this is a slightly more, you can say it's a more meticulous way of using calculus to find out the, and not using center of mass trick. Okay, you're just using fundamental calculus to understand how the tension varies with x. But again, like as you can see, this is totally unnecessary. At the exam level, you don't have to memorize the formula of tension, but just remember this concept that for whatever reason you're calculating in the case of a rotating rod, whether it is for stress or strain or whatever, if you want to find tension as a function of x, the easy way to remember it is just make an FBD of this section of the rod, which is of L minus x. Understand that it's rotating about this. So there is tension and centrifugal force acting on it. So this centrifugal force will act at its center of mass. Okay? So that centrifugal force will be equal to the mass of that section into omega square into position of its center of mass. If you just remember this, then it's very easy to directly work this out without doing an integration and without this proof and all that. Okay. Even this is a proof in itself because we are using fundamental concepts that we've learned before of center of mass. Only we are not having to do the integration because we are treating this section of the rod PQ which we have taken as a single rigid body and using the concept of center of mass in the dynamics on that. Okay, now once you got the stress, now for the strain we have to use differential element. Okay, we can't apply the Hooke's law directly to a whole section of the rod unless it's a differential section. So again, we will take this. Now we'll say that while it is rotating, this section has undergone some elongation. So it is dx plus delta of dx. This is a section of natural thickness dx, okay, under stress, and therefore elongated to dx plus delta dx. So it has a strain, longitudinal strain of delta dx by dx, because but you know this dt is actually negative, okay, because the tension is having a negative gradient with respect to x. So we apply Hooke's law, but before that, this. So stress upon strain is equal to Young's modulus. So this is the elongation that that small section is under. So the total elongation of the rod will be equal to so this is the answer to the second part, the extension. Just make a note of this, then we'll come to the third part, that is the elastic potential energy, which again we'll get from this kind of an integration only, using the formula of energy density, that energy density is equal to half stress into strain. Okay, so let's finish the third and final part. So the elastic potential energy. So once again, we can see that when we consider a volume element, now this time we will take that in the situation of this being in a state of elongation only, the thickness of this is dx. So it is having a volume of area into thickness. So the energy density which is stored in that region is half into stress into strain, which we can also write as half into stress square upon Young's modulus, because strain is equal to stress upon Young's modulus. Okay. So the stress, remember, was T by A. So it was m omega square by 2L into L square minus X square, this formula. So the energy density is this. Okay, so now the energy stored in that small section will be this energy density into its volume. So the elastic potential energy stored in this will be the elastic potential energy stored. Just have to solve this bracket and substitute finally. Yeah, sorry, the A will come in the denominator, okay, because it's stress square. Okay, yeah. So this A will actually come in the denominator. There's an A square here. So the final area that we get will come in the denominator, not here. Okay, now you can see it's dimensionally correct. There's an A square. Okay, so that is like an extreme example of the application of non-uniform stress and integration for calculation of elastic potential energy. Okay. Now moving on to concept of thermal stress, something that we have heard about earlier in thermal expansion but didn't explore. Okay, so this is longitudinal stress and strain due to thermal expansion or compression. So for example, suppose we have like a metallic bar, again of natural length L, area of cross section A, and Young's modulus Y. But they're sort of fixed between two rigid walls. So it's fixed between two rigid walls such that it just about fits between them without any stress at a certain temperature. So let's say this metallic rod also has a linear coefficient of expansion alpha, okay, and this has L naught is the natural length at temperature equal to theta naught, and L naught is also the distance between the two rigid walls. So that means at theta equal to theta naught, the tension in the rod is zero because the strain is zero. So the stress is zero. Now suppose we start increasing the temperature. The natural length of the rod would have become L naught 1 plus alpha delta theta. But because of the rigid walls, now it is subject in a compressed state, having still that length equal to L naught only. Because the walls will not allow it to move. So they are creating a compression of that much delta L from its natural length by applying this kind of normal contact force, which in turn will create a tension within the rod like this. So this tension due to thermal stress says that, okay, so the natural length is this, but the compressed length L prime is equal to L1. So the compression is the natural length minus the compressed length. Where alpha is the coefficient of linear expansion, is the temperature coefficient of linear expansion for the metal. So you can see that therefore the strain, the longitudinal strain it is under, is going to be now we can treat this as approximately alpha delta theta, because alpha delta theta is small compared to 1. So this is the longitudinal strain. Alpha delta theta is very small compared to 1. So therefore the stress this is here called thermal stress. So that is going to be Young's modulus into strain. So the thermal stress is going to be this must be precise, but approximately we can write that as just Young's modulus into alpha delta theta. So just for example, if we have a metal rod as above, okay, with area of cross section, let's say 10 centimeters square, natural length equal to 1 meter, okay, alpha equal to 5 into 10 raised to minus 6 per degree C, and Young's modulus equal to now if the stress is 0 at 25 degrees C, you want to find the stress, strain, and tension due to thermal stress at 75 degrees. Okay. So we can see that the strain is this much. So therefore, the stress so the tension So it's a pretty high amount of tension, like the weight of a 5,000 kg block, something in that kind of approximate range. So thermal stress can be something pretty significant, especially for thick rods. Like 10 centimeters square is quite a large cross-sectional area as far as metallic rod is concerned. So thermal stress can create quite a large amount of tension. The stress itself does not depend on area of cross-section. It's Young's modulus into alpha into delta theta. But the tension because of the stress is directly proportional to area. So the thicker the area of the rod and the larger the temperature difference that we are creating from the natural state, the stronger will be the tension developed. So as you know that to safeguard against developing this kind of stress, wherever there are metallic parts in heavy engineering, some amount of gap is left with sealant if required, but some kind of gap is left so that thermal expansion will not result in development of thermal stress and therefore very high amount of tension, which can also create otherwise bending and permanent deformity, even breakage, fracture, etc. This equation, of course, here has been written assuming that under the action of thermal stress, also the body is behaving elastically. So it is obeying or it is adhering to the Hooke's law. So that means the tension that is developing, and from that tension, the stress that it has, it is well within the elastic limit. So it's still behaving like an ideal material which is elastic in nature. It obeys Hooke's law. Okay, so this is the basic definition of thermal stress. Okay. Yes, Nikita, that's correct. The common example of railway tracks where gap is left, or even the case of, if you have a glass frame, a metallic frame for a glass pane or something. Okay, so there is always a bit of gap left which is filled with sealant, so that the glass will not crack, because the metal and the glass will expand at different rates. So you don't want to create thermal stress in the glass. Even glass will have some Young's modulus and stuff like that. So anyhow, so this is the basic formula of thermal stress. We'll discuss more questions related to this over a period of time. Now, the next thing we'll see before coming back to more complicated questions of thermal stress is how we deal with combination of materials when there is, this kind of longitudinal stress. So let's look at that with examples. Combinations of, you can say, longitudinal bodies under tensile stress and strain. So let's say we have a situation like this, where at the corner between a smooth floor and a rigid wall, we have kept, say, two metallic rods end to end, like a series combination basically. So this is rod 1. Its Young's modulus is this much. Its area of cross section is this much. Its natural length is, let's say, 2 meters. Now we've kept another rod. It's not really attached or something, it's just kept against this. So this is the second rod. It has a Young's modulus of, let's say, 6 into 10 raised power 11. Same area of cross section, and has a natural length of, say, 1.5 meters. Now, initially, the rods are at natural length. Then what is happening is at the point P over here, an external force is applied horizontally to push the system against the wall. So F external is applied such that the point P where it is applied displaces through a certain distance. Let's say it displaces through 0.6 millimeters. So you want to find how much this external forces, stress and strain in each rod, the elastic potential energy stored in each rod, and an equivalent Young's modulus for a single rod of natural length L1 plus L2 and area equal to A1 equal to A2, that will behave the same as this combination. So we want to replace this combination of two rods in series with a single rod which has the same geometrical dimensions as the combined rod. That is, it has a natural length of L1 plus L2 and common area of cross section E. Then what should be the equivalent Young's modulus for that? Okay. So just work out this question. You have to just make the free body diagrams of the rods, or you can also think of it like a force analysis. Okay, at the junction between the two rods, and at the point where we are applying the external force, you can analyze it that way also, and see how you will come up with some kind of equation to be able to calculate the required quantities. Okay, so what we have to understand is that when we are in that kind of compressed state, the junction point is in equilibrium because it is being pushed with equal amount of tension on both sides. So in fact, because the area of cross section is also equal, both the rods have to be under the action of same amount of stress. So this is the natural state. Now from this state, we want a situation where what is happening is something like this. Just a moment, we'll get back to that. Okay, so this is deformed in this kind of way, this kind of manner, such that the point where we are applying the force, that point has displaced from here all the way to here under the action of the external force. Of course, equal and opposite normal reaction acting from the wall. So this is the displacement that the point P has suffered. And as a result of this, you'll see that there is same amount of tension in both the rods. So stress in rod 1, stress in rod 2, so A1 is equal to A2 equal to so A. So now this was L1. So this is got compressed to L1 minus delta L1. And this was having natural length L2. So this has got compressed to L2 minus delta L2. So you can also see that T by A in the first rod is equal to Young's modulus into delta L1 by L1. And that is equal to T by A in the second rod. That is equal to Y2 into delta 2 by L2. And delta L1 plus delta L2 is equal to the displacement of the point. So now connecting this equation with these two, you can see that from equation 1, delta L1 is this much. And delta L2 and now equating with this. So this is the equation we'll solve to find the external force. And once we find that external force, so from that we can see that also we can see from these two equations, if we just take the ratio that Y1 delta L1 by L1 is equal to, so delta L1 is to delta L2 is equal to Y2 is to Y1 into L1 to L2. So in this case, the Young's modulus ratio were 3:1, and the natural length ratio Y2 is to Y1 was this, and L1 is to L2 is 2:1.5, 4/3. So delta L1 is to delta L2 is 1:4, and delta L1 plus delta L2 is the displacement of that point, which we have taken to be 0.6 mm. So delta L1 will be 1/5 of this, so 0.12 millimeters, and delta L2, the individual compressions of the rods will come out to be like this. And from this, you can see that the external force will become area of cross section into the displacement of the point P divided by this L1 by Y1 plus L2 by Y2. So the area of cross section was 5 centimeters square. The displacement of this point is 0.6 millimeter. And L1 was 2 meters, 1.5 meters. So 2 divided by 2 into 10 raised power 11 plus 1.5 divided by 6 into 10 raised power 11. So we can see that for the external force, take 3 into 10 raised power minus 7 into this 10 raised by 11 can come to the numerator. We have 1/1 by 4. 3 into 4 by 5 into 10 raised power 4 newtons. So 12 by 5 or 2.4 into 10 raised power 4 newtons. This is the amount of external force we are going to apply. That's the first part. Then the second part you can see is this, the individual compression of each of these. Okay. And third part is very simple. This formula that we have between external force and displacement of the point P, we just need to replace it with an equivalent rod of length L1 plus L2 and some equivalent Young's modulus. Yes, very good, Snikita. That's correct. Okay. So this is like a very typical type of question at even JEE mains level, and we will discuss a couple of shortcut tricks also in the next lecture in how we can simplify these problems by comparing the given situations of the combination of rods, like a combination of equivalent springs. So we can see that within elastic limit, the longitudinal elasticity of a material makes it behave like an ideal spring. Like an ideal spring has a spring constant K. This kind of longitudinal material has an equivalent force constant of AY by L, where A is the Young's, area of cross section, Y is the Young's modulus, and L is the length. So we can replace this kind of longitudinal material with an equivalent spring of force constant AY by L. So this is like a series combination of two springs. So we can also do the problem that way. Is to the whole thing of equivalent spring constant. Sorry, for equivalent Young's modulus, you can see that you want a single rod of length L1 plus L2 equal to that area of cross section with some equivalent Young's modulus, so that the same amount of force will produce the same amount of delta F. So we had this above equation L1 by Y1 was equal to the displacement of the point P. So we can say that now the same amount of force, the same amount of area of cross section divided by L divided by into L divided by some equivalent Young's modulus should give us delta L, which is equal to this. This is L1 plus L2. So ultimately, you can see that what we'll get is that L1 plus L2 upon equivalent Young's modulus should be equal to L1 by Y1 plus L2 by Y2. So the equivalent Young's modulus will become L1 plus L2 upon L1 by Y1 plus L2 by Y2, which you can see as the dimension of Young's modulus. Okay. So for example, if there were two materials having the same value of length L1 and L2, then the equivalent Young's modulus would have been Y1 Y2 divided by Y1 plus Y2. But here, if they are having different lengths, so then L1 L2 is also coming into the picture. So this is the third part for the equivalent Young's modulus. Yeah, so you can just substitute in this formula and verify. I think L1 L2 were 2 and 1.5, and Y1 and Y2 were 2 into 10 raised by 11 and 6 into 10 raised by 11. So by substituting, we get the value. Okay, people. So hope this part is clear. So with this, we conclude today's session for properties of matter. Still some things to do in properties of matter, but you can say the major numerical analysis part is almost done. So you should be able to solve questions related to this. Next time we will look at some more tricks of solving problems, like converting longitudinal materials into equivalent springs with some spring constant and all that. And then we will also look at elasticity beyond, or rather stress and strain beyond that. So that's why I said that this part of properties of matter is mostly done. And on completion of this, we will of course start with the fluid properties, the non-ideal fluids, that is viscosity and surface tension. So these are the things coming up in the next lecture. So that's it for today's session, people. Wish you all the best. Yeah, after completion of this part now, surface tension and viscosity, we'll discuss the doubts from the module in one session. I mean, it's an easy chapter, so it should not take that much time to discuss the doubts. Okay, Vineet.